This project is production grade. We are going to build a data pipeline that turns a raw stream of data into this dashboard. To make it production grade, we are also going to implement star schema and delta lake to store our data tables. And here's the best part. Everything in this project from the beginning to the end is real time. The data arrives in stream that never ends. The data processing is real time. And the dashboard that we create adapts to the data changes. And by the way, you can get access to every resource that I'm going to use in this project through the links in the description. Without further ado, let's begin.
In this video, we're going to work on the project named Live Traffic Analytics. Just by the name, you would have already anticipated that we are working on something closely related to road traffic. And you're right, the data that we're going to work on comes from different locations of a city, which has average speed of a vehicle in that particular area and what kind of area is that and what road is that, and we determine the driving conditions of that particular area. So we do that in multiple areas of a city. So it is basically like estimating the driving conditions in different locations of a city and also by the weather of that location. So we are going to work on something related to that. And our main audience of this project includes the city traffic control authorities who basically work with this data to determine those traffic conditions in different locations, and also ride-sharing applications like Uber, Lyft, or some sort of applications like that. And yeah, those are our primary audience basically. And this right here is our whole architecture of this project. Basically our data pipeline that we are going to follow to complete this project. Our data pipeline starts with the data source, and this data source will not be a static one. It will be real time. It generates records for every few seconds, which means we're not going to use any static CSV or JSON files as our data source. We will be using a Python code alongside Faker and a few algorithms that generates this data, which also ingests some faulty data into our records, which will later be cleaned in the data processing stage. In that way, we get never-ending data until we interrupt the execution, and we also get the data to look or to mock the real-time data, the real-world data with the faulty data as well. And this data will later be streamed using Kafka as our data streaming engine. And this is the stage here. So it will be streamed through Kafka as a data streaming engine, which later be taken out for the data processing. And we will be using Apache Spark for our data processing tool. And we will be processing this data in 3 stages: bronze, silver, and gold. And this data storage architecture, bronze, silver, and gold, is called as medallion storage architecture, which I already mentioned in a lot of my videos, but if you don't know, I just wanted to repeat it. Okay. Yes, this data from Kafka will be pulled out from Kafka using Apache Spark, and then will be saved right away just by assigning the schema to that data in this bronze layer, which will be this one, the bronze layer, the raw data layer. And later, we pull the data out again from the bronze layer and we clean the data just by removing the faulty data from it, and then we store that data in silver layer, which is our second stage of processing. So that will be the clean data, and this clean data will later be taken out, and that data will be gone through a few data transformations like our aggregations to make it business ready, and then will be saved in the last stage of our storage, which is gold layer, this one. And this throughout this whole storage of this data, we store this data in Delta Lake format, and that is why I use this icon right here. I tried to put it somewhere else, but I can't figure out where to, so I just put it aside. So when I explain it, I can just explain I stored the data in Delta Lake format. Okay, and with that, the data processing will be done. After that, we're going to use Hive Meta Store as our metadata database. Okay, that will be our metadata database, which means we are now going to save this data inside that database. This data is basically stored in the Delta Lake. Like I said, the Delta Lake, but we use Hive Metastore as our metadata database, which means we only save the table's metadata, like the table name, table schema, and the location of that table's data where it is stored, which is in this Delta Lake, the storage, the storage location. That metadata will be saved in this database. And then later we connect this metastore to Power BI so we can get access to that tables, the goal tables in the Power BI so that we can create the dashboards later with that data. That is the end of this whole pipeline. Before beginning with the project, I want to emphasize one thing. When I said we are going to use Apache Spark as our data processor, you might thought we are going to use Databricks to run these Spark jobs to process the data. But no, what we are going to do is we are going to create containers in Docker. So we are going to set the whole infrastructure in our local computer without using Databricks. And there are a few reasons for that. The first one is when I recently created a free trial account, I realized Databricks, I think Databricks reduce the privileges for that free trial users where we can't actually have the whole look of Spark UI. I tried to, but I didn't find a way to actually look at the Spark UI. So I think they reduce the privileges in the free trial account alone. So still, you can do everything that we're going to do in this project in Databricks. And it is a lot easier than this because here we're going to set the whole infra up and there are a lot of stuff to deal with. But there, it is already abstracted. So you can just copy paste the code and run it. It is it is a lot simpler in Databricks than this. But if you want to follow this, you can go with this. That's up to you. To begin with, we need to install Docker Desktop on our PC. If you never install Docker Desktop, it is pretty simple. I'm going to show you how to install it. Just head to any web browser and search for Docker Desktop and click on the first link. I will provide the links that I'm going to use for in this project, the tool links and also the GitHub links, which have all the codes and files that I'm going to use in this project will be in that GitHub repository. And here you just hover on download Docker Desktop button. When you hover it, you'll see multiple options and you pick the one that fits you and download it. And while installation, just keep all the settings by default and just install it. So we need this. If you're using the way I'm using, if you're going with the way I'm going, because I'm going to set the whole infra in Docker, like I said. If you are not going to use Docker, don't install it. I recommend you to install it because we are going to set Kafka as well in Docker itself. So it is better to, go with the process. We create containers for Kafka, Spark, and Hive Metastore, all of them. After installing Docker, This will be the page that you will be landing on. This is basically the home page. All the containers that we create will be visualized in this page. And by the way, you don't have to sign up or sign in. It's totally up to you. Either way, it works. So keep it in the background. Now, with that, we don't need it, but this tool I'm going to say now is not necessary to even to establish the infra, but it makes our work a lot easier, which is VS Code. I know I talked about these tools a lot of times in my videos. If you're an old audience for this channel, you would have already heard of this verse 100 times, but still, for the new viewers that are just visiting our channel, I'm going to talk about every single thing. This is just a code editor, so it makes code editing and file creation a lot easier than using a file manager and notepad to create files. So we use that. And installing this tool is also simple. Just go to any web browser and search for Visual Studio Code Editor and click install and install with default settings. That's it. Also minimize this to the background. Now go to C drive. You don't have to basically. Open PowerShell. Now we create a project repository for our project. And I'm going to name our repository as to keep it short and simple, I'm going to name it mobility. And again, if you never use CLI, what we are doing here is we're just creating a folder named mobility. The full form, the abbreviation of mkdir is make directory. So we use mkdir mobility to create a folder, and the folder is created at this location. So that is how CLI works. Whatever actions you do will be reflected to this locations, this particular location. You can also change that location just by typing this command. cd stands for change directory. You can just change directories back and forth. cd mobility. Now our directory is switched to mobility. Now whatever I do here will be reflected to this location. So in C drive, because it's a C users, and the username, here we created a folder named mobility right here. That's how it works. So it's basically making the process a lot faster and simpler. That's it. So we created the folder. Next, we're going to connect that folder to the VS Code. Open VS Code and click on Open Folder. Choose the folder that we just created, which is mobility. Select that. Yes. Okay, now from here on, we're going to create files in VS Code and not command prompt or PowerShell. So our first file should be Docker Compose file. This will be the Docker Compose file. Here we define all the containers we are going to open for all the tools that we're going to use, which includes Kafka, Spark, and Hive Meta store. We define them and we run them, so Docker opens those containers for us. And for this, I have the code already written somewhere, so I'm going to copy paste it and explain what we're dealing with. Mobility. This is the one. Okay. Here, First, we defined a PostgreSQL database, which later we will be using as our metadata database with the image Postgres 13 and the container name as Hive Meta DB. And these are the environment variables that we are going to use. We will not be using, but we define them anyway. The database name, the user, and the password, and the port to access the database. And the next service is Hive Metastore, which will be our actual Hive Metastore service. With I downloaded that image using Apache Hive 3.1.3. That is the version of that image. If you don't know how this Docker works, we basically are going to run these applications instead of actually accessing them online with any other platforms. We are going to run them in our local computer using these images. We just download these images and run these as containers in Docker, and we can just access them as normal services. Basically, mostly offline. And this will be the container name Hive Metastore, and it depends on Postgres Meta Store, which is our database, the Metastore database, Postgres Metastore. And then we define some environment variables, which is service name, Metastore, DB driver, Postgres, and is resume is false. I will talk about this. No, I'm going to explain it now itself, all right? So what is resume is, when you turn these containers up using a command, which is docker compose up, when you turn these containers up, it creates, this Hive Metastore creates this service, this database, when you turn it up. And after you turn these containers up, if you want to pause those containers, let's say you turn these containers up and you got some work to do and you want to shut the PC down. Okay, when you shut the PC down, basically these containers will also pause, right? So when you want to when you want to resume all these containers again after you open the PC, you can just click on the resume button in the Docker desktop right here. I will show you how. And all the containers, actually most of them will turn up, but this Hive Metastore will not turn up because it again try to initialize the database, the Metastore database, and it fails because it already created one when we turn the container up at the beginning. That's why to actually turn this container up again without initialization, we say is resume as true. Right now we leave it as false because we haven't run docker compose up. We haven't turned these containers up at all, so we leave it as false. But when we pause it and we want to resume it again, then we change we switch this to true, and then we resume it, then it will resume. That's how it works. I will actually demonstrate it. Okay, and this is the port that this Metastore is exposed to, 9083 9083, and these are the volumes it has access to. So we mount these volumes to that containers. So these containers have access to only these volumes. They can save data. They can read data. They can write data. So yeah, the back and forth operations, they can have access to that volumes. Later, the next one is Spark Master. If you know about Spark, we actually have a Spark Master. We'll have a Spark Worker, a Spark. Is that Spark Manager? Wait. Okay. So the basic architecture of Spark will be there will be a driver who actually parses the Spark code and distribute the work among them. So there will be a Spark driver and there can be multiple Spark workers. So there should be one driver. It is like a master slave architecture, right? If you already know about it. But if you haven't heard of Spark at all before, I would highly recommend you to go check the Spark masterclass that I've done a few months ago. I explained every single thing about Spark, including the architecture and how it works in the backend, all of it. So the basic architecture is like Spark has a cluster manager, a driver, and a few workers. A cluster manager is the one who distributes, not distributes, who actually provides the resources to the driver and the workers. All right. And here, the Spark cluster manager is named as Spark Master. This is the one that is responsible to supply the resources to the workers and the drivers. All right. And the Spark worker is this container. We basically will not create a separate container for Spark driver and worker because we can actually create multiple Spark workers. And while the time we run the Spark session, if we run a Spark session in one particular Spark worker, that worker will act as a driver and a worker as well. So we usually don't actually create a separate container for a driver, but we can if we want to. So that driver, the only job for that driver is to parse the data, parse the code, and then distribute the work across the workers. And the workers are the one who executes the work. Right now, we have one Spark master. The container name is Spark master, which is the cluster manager, host name, and bash spark master.sh. And then these are the two ports that we expose this container to, and one port is for the Spark master. Right when we turn this container up, we can actually see the Spark master UI. Spark master UI is not an actual Spark UI. In Spark master UI, we can actually see the resources that are available and the tasks that are occupying these resources and the tasks that are waiting to get the resources, everything. So we basically see how the cluster manager manages these resources with a UI. So by this port, we can access the UI. This port is just to connect, just like a listener port. And these are the volumes that this Spark master will have access to. Warehouse, apps, and Spark IV. Spark IV is to basically store all the packages that we download when we are going to download a few jar files and stuff like that when we actually connect to Spark SQL. And I will point this out at that particular time. And apps is where we store our transformation codes, the .py PySpark codes. So to access those codes, this volume should be mounted to Spark master as well as Spark worker. And we have Spark warehouse is where we store the data. We actually store the delta tables in warehouse folder. And then we have Spark worker, which acts as a Spark driver and worker all alone. And there's the image, there's the version. And here's the best thing. No matter no matter when you run this project, maybe a few months after or a few years later, you don't have to search for the same versions again because I already typed the particular versions that I'm going to work in this project right here. So you can just download that versions and do the project. So the project will not break when you try to install these later in the future. But if you want the latest version of all of these, instead of typing the precise version number, you can just say latest and it downloads the latest image if you want the latest one. but the execution might be slightly different because that might get a few changes in those updates. And the host name, Spark worker, and the command and the ports that it is exposed to. Here, this 4040 will be acting as our Spark UI, because this worker will also be as our Spark driver. This port will be a Spark UI. We can see the task and the jobs that are running, even the SQL jobs and the Hive data as well. This will be the Spark UI navigation port, and this will be our thrift connection. A thrift when we establish a thrift connection, we are going to use this port. I will tell you what that is when we get to that. When we get to connecting the Metastore to Power BI, we use thrift Metastore for that. And then this Spark worker depends on Spark master, because that is the one responsible to allocate the resources. And of course, this should also be mounted with the volumes warehouse, where we store the data, apps, where we store the transformation code, and Spark IV, where we store the packages that we need to run the project. With that, the Spark infra is done. We just have one master, which is our cluster manager, and one worker. No other workers, but if you want to add more workers, you can just add one more thing underneath here. Just by removing these ports, we just need one port, because that will be just acting as worker and not driver. And yeah, you can also attach one more worker if you want to make the process faster. But for now, we don't need, because we're not going to actually work on big data, but we're just mocking that big data. So we're just going to take a chunk of data and work on it. Now, the next container is Kafka. For this, the first image is actual Kafka. Here we get the latest version. Like I said, we can actually mention the precise version of it here, or we can just say latest, and it downloads the latest image version of that Kafka. I might just change this to the version that we worked here. We work in this project, so if you want to do the project later in the future, you don't get any errors because the version is changed. I might change that later, but for now that's fine. Container name is Kafka, and the ports 9092 and 29092, which will be the listeners. And yeah. Yep, these are the two listeners. These two ports are the listeners. And then we have Kafka UI. So we not just have this container, we also have Kafka UI. And it is up to you to actually open a container for Kafka UI. We're not going to use this Kafka UI much, but I'm using this. I'm actually turning this up just to show you how Kafka captures the data. Even if you never define Kafka UI, you can still do the project with just Kafka alone. Kafka UI is just for us to monitor it. Here we use Provectus Labs Kafka UI. There are a lot other Kafka UIs as well, like Kafdrop, but you can use either of them. I chosen Provectus Labs Kafka UI. I download the image for that and create a container, and this is the port that we can access Kafka UI at. And then it depends on Kafka because this is Kafka UI. And that's it. So with that, we're going to create how many? Like 6 containers. So we save this file, go to PowerShell. From here, run docker compose -d. Docker compose up will turn the containers up, and Docker compose down will shut the containers down. And this flag at the end, -d, is not necessary, but if you don't use it, this CLI will be dedicated to show the logs of those containers. But if you use it, when you run this command, it just turns the containers up and detaches. So -d, flag -d stands for detach. So when we run it, it just detaches. That's it. Wait, failed to create shim OCI. Something went wrong. Okay. So this is the thing. I think, let me see. Okay, so now this is false. Let me switch it to true. And run that again. Wait, so that is not the error. Let me debug it. I just remember there is one more step we have to do before we actually turn the containers up. And that is, we have to create a folder named Hive config like this. So let me delete this first and do that whole thing again so you can just follow up, right? And what we have to do is we have to create a new file. Okay, first the new folder named Hive config with this Hive config, new folder with Hive config, and then inside that folder you have to create a file named hive site.xml. This one. Create that file, and you can find this file in the GitHub repository. All right, you can just copy paste that file. But here I have the file with me, so I'm going to open with. I'm going to open with the notepad and just copy paste it. Copy, paste it here, save it. We need this file to initialize the Hive Meta store service. Without this, we cannot. So this file is also mandatory, just this one. Now close this. And this can be false because is resume can be false. At the initial stage, this can be false. After, when you pause and resume it, you have to turn this to true. But now, it'll stay false, and then run the command again. Docker compose up. Okay, now we did not get the error, and in Docker, the container is up and running, right? And this initialization should only be done once, like I said. When you have a work and want to stop these containers or pause these containers and then run them back again, resume them back again later, let me show you. So if you just pause these containers or stop them and want to resume them, maybe running the same command again, right? Every other container, oh wait, let me stop them. Will that work? Okay, we stopped all the containers. right? Now we run docker compose up. Every other container starts running again, but Hive Metastore stops. It fails to run because we already initialized it, so it should not initialize again. So what we have to do is we have to turn this to true. So we only need to put is resume as false at the first initialization step. After that, we say true and then turn the container up. Now it runs. I can just go ahead and do the rest of the steps without mentioning this part. But when you run and we obviously take breaks in the middle of a project, right? We can't do that in one go. So when you pause it and try to play it again, you might end up being stuck and losing all the data if you shut the whole container down. You don't want to do that, right? So instead, we do that to pause it and resume it again. With that, our infra is ready to go. We have all the containers that we need. So let's head to the next step. Well, now we begin with our first layer of our data pipeline, which is the data source. We have the whole infra ready now. So the first step is setting up the data source. Like I said, we're not going to use any static files as our data source, right? We are going to use a Python code. So I have that Python code written already, and I don't think I have to type the whole code in here because that is just a data source, right? So I have the code, but I'm going to explain how the Python code works, and so we know what data we are working with. All right. Okay. Let me head to that. For that, I'm going to create another folder. And by the way, you might be wondering, we haven't created these folders by ourselves. Remember, we never created apps, Spark, IV, but warehouse. But what we did is, in our Docker Compose file, we mounted these uh, folders to the containers, the Spark master and Spark worker. Remember, apps, warehouse, Spark IV, we mounted them, but we never actually created them. But when we turn these containers up, these folders will automatically be created when we turn the containers up, basically, because we don't have the folders, so they'll be created automatically. Okay, now we are going to create another folder, the new one, with the name producer and a code. I already have the Python code, like I said. Producer. Say traffic. Dirty. Producer.py. Create that file and copy paste whatever is in this file. Open with a notepad. Copy that. Close all this. We don't need them. Paste it here. And this is a Python file that we are going to run that generates the data and send these records to Kafka to stream it. So yeah, before going further, we have to have an idea of the data that we're working with, right? So yeah, let's begin with that. Firstly, we're going to import all the libraries that we need to generate the data, which includes Kafka. From Kafka, we import Kafka producer because we're going to connect to Kafka and act as a producer. This code will be acting as a producer to produce the data. So import that, and we import from Faker, import Faker. to fake the data, to generate fake data. So we use faker here to generate the fake data. And then we import JSON to, because we're going to work with JSON files. We're going to convert the data as JSON file and send it through Kafka. We need JSON. We need to import JSON, and then we import random to pick a random integer or a decimal or any number in between the range. We are going to use random to pick randomly. And then we import time. And then we import from datetime, import datetime and time delta. Datetime is to is used to work with time, and also time delta as well. We use time delta to actually add or subtract the time from a time. Basically, we will use it, and I will point that out at that particular moment. And then we have import pytz. This is also something related to time. We will use it. Now the first line, fake equals faker. So we're going to assign faker off to a variable named fake. That's it. And then here we initialize the producer with the variable name producer as Kafka producer, and bootstrap servers equals localhost 29092. That is the server, that is the port for our Kafka. That is our listener. Wait, yeah, 29092. This is our listener. I think it is the advertised listener right here. So we connect to Kafka through this port, and then we use value serializer lambda v json.dumpsof v.encode utf8 encode of utf8. Basically, by the end of this iteration or one iteration, we will have a dictionary of data that we are going to send, right? What we're going to do is we're going to convert that dictionary into a JSON file using json.dumpsof. We use json.dumpsof to convert a dictionary into a JSON string, and we use JSON loadof to convert a JSON back to a dictionary. So it is easier to send the data in JSON format rather than dictionary. So we convert it into a JSON format, and then we encode it to UTF-8. Basically, whatever the data that you stream in through Kafka cannot be streamed as strings. It can only be streamed in bytes. So we encode it into bytes using .encode of. So that will be converted to bytes. And then at the receiver side, at the consumer side, when we consume the data again at the bronze stage of the data processing, we will decode this bytes into actual data later. So that is how value serializer works. We serialize the data. Okay, now we create three lists. Roads with road numbers, random road IDs basically. We have 4 road IDs, and zones, CBD, commercial district. I think CBD stands for something. Let me see. Okay. Yeah. So CBD stands for Central Business District, which basically refer to a busy area where all this commercial stuff are located. And airport, we all know what airport is, and tech park like IT hubs, something like that, and suburb is like the outskirts of the city. And then the train stations where the trains stop. So we have all these zones. And the weather conditions, we have 4 different variants of weathers: clear sky, rain, fog, and storm. So we have these 3 lists created. We can add, if you want to have more varieties of data, you can actually add to these lists. And then we create vehicle catch as an empty list. We will use it later, but we just created one empty list. Now our first definition is generate clean event. This function, whenever this function is called, it generates one record for every function call. So once it is called, it generates one record. The first one it does is vid equals fake.uuid4. So it creates a fake ID. It generates a fake ID and assigns it to vid. It will be a 16 digit characters. I think it is 16 characters long, the ID that gets generated. And then this vid will be appended to this list. So we actually connect all these vehicle IDs, which we will be using later to when we ingest the fall data. But for now, this is what we do. We just append these vehicle IDs alone to this list, vehicle catch. And then this function returns vehicle ID, which is vid fake.uuid4, and then road ID, which will be random.choice of roads. Random.choice of roads. Roads is the list that we defined before, right? And random.choice of, actually this method actually picks a random element from a given list. So here we gave a list named roads, so it picks a random element from these 4 objects basically. So for every iteration it will be random, it'll pick a random object from that list. Then we have city zone. This use the same logic. Random.choice of zones, it picks a random object from this zones list, which has like 5 objects. And then we have speed. For speed, we use a random.randint of 20, 100. This is quite different, but similar to random.choice of. Here, when we say random.randint of, and we define a particular range, which here is 20 to 100, so it picks a random integer in the given range, 20 to 100. And then we have congestion level. Random.randint of the same logic, 1 to 5. So it picks a random integer from 1 to 5. And until now, you know vehicle IDs, right? What is vehicle ID? We just assign an ID for vehicle, that is vehicle ID, and the road ID is ID of a road, which we define. And city zone is the zones in the city, basically. The airport, tech park, and CBD, suburb. Speed is how fast this vehicle is moving. But what is congestion level? Congestion level is nothing but a rating from 1 to 5 to rate how crowded is that particular location is. If the rating, the congestion level is 1, the traffic is so low, it can be freely flown through. And if it is 2 or 3 or 4, as it goes up, the traffic density is increasing. Basically, defining the traffic density. That is how congestion level works here. So we rate it from 1 to 5. And then weather, random.choice of. So it picks a random object from the list, weather. And then event time, datetime.now of pytz.utc universal time .iso format. So it picks, it doesn't pick, it just retrieves the present time in universal time format. That's it. And assigns to event time. With that, we have one record. And then we have another definition, def generate dirty event. This generates a clean event, and this generates a dirty event. And this goes like dirty type equals random.choice of. So whenever this function is called, it picks a random fault from this choice. So the dirty type So it picks a random dot choice of and the list of dirty data options, which includes null speed, negative speed, extreme speed, duplicate vehicle, late event, future event, wrong data type, schema drift, and corrupt JSON. So it picks a random error from this, and then after picking one, we assign generate clean event of. Oh, wait. So when this function is called, it will pick one from this list, like I said. After that, it creates a variable named base, and then it calls the function generate clean event, which is this one. So it generates an event, a clean event, and assign it to base, that particular dictionary. So it creates one record in dictionary format and it assigns to base. After that, based on the dirty type it picks using random, that particular dirty data will be ingested into that particular record. If the dirty type is null speed, base of speed. So this is how we refer any key in a dictionary, right? So a dictionary is basically a key value pairs, right? And when you want to refer to a value, we refer to that value using the key that is assigned to that value. Here, base of speed is nothing but referring to the value with the key speed. So base of speed equals null. So the value will be converted to none, not null. So that will be assigned to none. Else if dirty type equals negative speed, base of speed, the same key, is assigned with negative speed, which is minus 40. And the same thing, else if dirty type equals extreme speed, base of speed equals 420, which is extreme speed. It doesn't make any sense to have 420 as a speed. And then we have another dirty type equals duplicate vehicle. And here is where we use vehicle catch from before, where we saved all the vehicle IDs, right? Not all of them, just this particular vehicle ID that gets generated for that particular record. So we save that in vehicle catch, right? Else if the dirty type is duplicate vehicle, base of vehicle ID equals random dot choice of vehicle underscore catch. So it stores all the vehicle IDs that gets generated in the previous records as well, and this particular record's vehicle ID will be assigned with the past vehicle ID that gets generated. So it creates duplicate vehicle IDs. And then we have else if dirty type equals late event, base of event time, date time dot now of pytz dot utc minus time delta. This is where we use time delta to subtract from the time delta, and we subtract the time with minutes. Minutes equals random dot rand int of 10 to 120 dot iso format, and this will make that event 10 to 120 minutes old. So that will be considered as a late event. Basically, when you work with some kind of data like this, like a time related data, you don't want the event to be 10 or 120 minutes old, right? Because this is something, this data is something related to the traffic. And if it is 10 minutes old, the traffic conditions would have been already changed a lot. So that doesn't work. So we exclude that late events. So we have to exclude that. So any late events will be what? Fall data, right? That's what we're doing here. And then else if dirty type equals future event, that is late event and this is future event. Future event also doesn't make any sense. What we do here is base of event time, date time dot now, the present time, plus time delta of 5 to 60 minutes. We add 5 to 60 minutes to that time delta, to that particular time, which will be the future time. And that doesn't make any sense as well. Else if dirty type equals wrong data type, base of speed equals fast. So the speed is supposed to be integer. So when we assign a string which is fast to it, that will be the faulty data as well. And then we have else if dirty type schema drift, base of road condition equals random dot choice of good, bad, under construction. So the road condition, the schema drift, all right. So right now we only have these columns, right? We only plan to do these columns: vehicle ID, road ID, city zone. How many of them? 7 of these columns. But in schema drift, we are going to add another column, which is road condition. That will be a schema drift. That breaks all the schema. So that will be a schema drift. This column should be taken out. And then else if dirty type corrupt JSON, return corrupt event. Till now, in the previous errors, we just replace a column or add a new column with the faulty data, right? But here, what we're going to do is we are going to take the whole record out and replace it with this string saying corrupt event. So it actually doesn't generate an event at all. It only generates a string that says corrupted event. That's it. That is how it works. And after ingestion, after this appropriate fault data ingestion, this will be returned, the base. The final record will be returned, the dictionary. With that, we have our next function generate dirty event as well defined. Now, this is the part where we execute these functions. We open a loop, basically an infinite loop, using while true. While true opens an infinite loop because it doesn't have any condition. So every time it loops and checks for the condition, it is true. So it just loops infinite times. And we have an if condition. If random dot random of this particular one, this generates a random decimal number from 0 to 1. Okay, we generate that to make sure the fault data is like 30% of the times, and the 70% of the data should be clean. So if the random dot random of is less than 0.73, generate a clean event. So we say event equals generate clean event. Else, if that is more than 0.7, anywhere around 0.7 to 1, then in that 30% of chance, generate a dirty event. So it calls this dirty event function, or else it calls the clean event function alone. So it only generates a clean record, and the 30% of times it generates dirty event. Okay, and then if is instance event comma string, so it checks if the event that we get is a string. Is instance event string. So if the event that we get is string, like the corrupt, like this one, you see, corrupt event is a string, it is not a dictionary. So it checks for that. If the event is a string, producer.send of traffic topic, which will be our Kafka topic, which we send the data to stream. This will be the Kafka topic name, and then value raw event. Print corrupt event sent. This is for the corrupt event, just for this possibility. Just for this one, we have a logic here. And anything else, if that event is not string, it obviously is a dictionary, right? There are only two possibilities. And if it is a dictionary, that is a normal event. So do producer.sendoff to the same topic, value equals event, just the event. Print event. That's it. Now, this while loop, instead of looping over and over again without any time breaks, what we're going to do is we use time.sleep off to make this loop sleep for every iterations, between every iterations, and the sleep time will be random.uniform of 0.5 comma 1.5. So it picks a decimal number. Random.randint picks a random integer in the range, and random.uniform picks a random decimal number in the range 0.5 to 1.5. Basically, 0.5 refers to half second, and 1.5 refers to 1.5 second. So it picks the sleep time anywhere between that range, and delays the next loop with that time. That's how our real-time data streaming works. Next, we run this and generate the data, and we move on to the next part. And for our next stage, we have Kafka data streaming. We're done with data source. We have our Python code ready. Oh, sorry for that ugly circle. So we have that data source ready. We have the Python code. We just have to run it so it generates the data. Now we are going to talk about data streaming using Kafka. Even for the data streaming stage, we already have the infra ready. We already have the containers that runs the Kafka. We just have to run this Python code that generates the data and sends or streams them using this Kafka streaming engine. Let's do that. Let's open Docker first and open the UI that we talked about, Kafka UI. In this Kafka UI, let me try to zoom this in. Okay, for some reason I cannot zoom it, but I hope you can see it. Okay, so this is Kafka UI container, right? And the port that this Kafka UI is exposed is 8090, this one. So click on this port, and this redirects to the Kafka UI. Right now it says, so this is a UI for Apache Kafka, and this is the dashboard, one online cluster and brokers, and the topics. We haven't have any topics created yet, and the brokers, consumers, we don't have any consumers yet too. So first thing we have to do before we stream is we create a topic. So let's create a topic. We open PowerShell and we run a command in this. Let me zoom this in so you can actually see it. I hope you can see the CLI. The first thing we have to do is Docker. Now, exec. So because the container is running inside Docker, we have to say run this inside the container. So we use docker execute to execute it inside a Docker container. And this flag, IT, stands for interactive terminal. And then the one we are going to run, the container name that we're going to run, this command is inside Kafka. So we say Kafka and opt. Kafka bin. And by the way, in order to complete this whole project, we are going to run a lot of commands. and I can type it here, a few commands, but not every one of them. So for you, instead of you actually looking at these commands and typing by yourself, what I'm going to do is I'm going to type all the commands in a text document and upload it to the GitHub repository, so you can just have access to it and copy paste all these commands, so you don't have to type them in. It is a lot of work to type them in. This, we haven't get to the main part yet. These commands are so small. These are easy to type in, but as we go, the commands get bigger and bigger with additional packages which are linked to that commands. So it's not easy to type the whole command in. In that case, you can just use that. Topic. The topic name is traffic topic, and the server (9092). And the partition as 3. When it comes to partitions in Kafka, we basically are, they are basically the partitions. It is a long topic to explain, but if you're interested in Kafka and want to know more about Kafka, I already done a masterclass as well on Kafka a few months ago, and I leave the link for Kafka and PySpark in this video description. You can just check those videos out. There are a few advantages of separating these, the topic into partitions, and there are a lot of them. I cannot just explain it in this video because this becomes a masterclass as well. But yeah, but for now, we're just creating a topic with, we can just create this with one partition as well. That works too. Replication factor as 1. Run it. What happened? Okay, so you see, this command is simple, and I already done a typo here. So what I'm going to do is I'm going to paste this here. All I did is I forgot to add an S at the end. It should be Kafka topics.sh. Basically, these images have a lot of these files saved inside the containers, and we have to direct, or we have to navigate to that particular bash file. So these .sh files are nothing but bash files. We have to navigate to those files appropriately to actually work with that tool. So here I'm creating a Kafka topic, so I have to navigate to Kafka topic.sh. In the same way, there are a lot of bash files depending on what action we are going to take in Kafka, and we have to navigate to that particular bash file. Okay, we have this ready. Now let me copy paste it again. Now this works. There you go. This should be the output. It says created topic traffic topic. So when you refresh this, refresh. Okay, well, it doesn't list the topic here, but maybe when we actually send the data into the topic, oh, there you go. Now it is here. Okay, it took a few seconds to reflect. There you go. So that the topic name is traffic topic, partitions 3, replication factor 1, and size 0 because the number of messages sent is 0. We haven't sent any messages yet. Now we have the topic ready. The next step is to run the Python code. Now, to download the dependencies first for that Python code. First, you need to install using pip install Kafka Python. This is a Python to Kafka connector. You need to install that. And what am I typing? Faker. You need to install Faker as well. And alongside, you need pytz. You need to install all these 3 dependencies. I already installed them in my computer, so they're going to say they already exist. There you go. So it says requirement already satisfied. But if you haven't installed them yet, it takes a few seconds to install all these requirements. And now type in cd producer. That is the folder where we saved our Python data generator file. So type and copy this file name and run it. Say Python and the file name .py, traffic dirty producer.py. Run it. That is the confirmation. If you haven't got any errors and you can actually see all the columns, all the records one after another getting generated, that is how you confirm the code is working. Well, this is a copy paste code, so nothing goes wrong unless the infra goes wrong. The infra is correct, so the code runs perfectly. So you see, if you take a look, these are one columns getting generated at a time. So this is one column. This is, no, not columns, one record. This is one record, and this is one record. And there you go. This is the corrupt event sent. That is the fault data that we simulated. You can keep this running, but I cannot because I have to explain all the codes and it takes a few minutes to explain. So if I keep this running in the background, it can generate millions of records. So I don't want to keep it going. So to interrupt it, you simply hold Control and click C, Control plus C, and that will interrupt the process like that. Now, when you head to Kafka UI, right here, refresh. So in that small amount of time, it already generated 78 messages. 78. And if you click on the topic and switch to messages, you can actually see all the messages that got generated. See that? And all these messages are divided among the partitions because we have 3 partitions, right? 0, 1, 2. And these messages are divided among those 26, 28, 24. Okay, we have the data streaming in Kafka. Kafka can hold this data for a little longer. Before it gets expired, we have to pull the data out and we have to save it in bronze storage location as a delta table, the bronze delta table, basically. With that, we are done with real-time, the data source and the Kafka data streaming. And our next stage is bronze raw data stage. We use Spark to pull the data out of the Kafka stream and assign a schema to that data and save it in the bronze layer as a delta table. Let's head to that. All right. As part of our first step in the data processing, like I said, we're not going to do any cleaning or aggregations in this step. We're just going to get the data out of Kafka and assign a schema to it. So we create a file, a .py file under apps, because apps, the folder apps is mounted to the Spark worker and master containers. So we are going to create the .py files here under apps. Create a new file and name it something. I'm going to name it traffic bronze.py, because that is part of the bronze part of transformation. Now we're going to import some requirements here, required libraries, say PySpark .sql import Spark session. We first need to open a Spark session to create a job, right? So we need to import Spark session library for that. After that, we need from PySpark.sql.functions, and I'm going to import all the functions that are available. So we don't need to bother about importing one at a time. Then from PySpark.sql.types import all. We need these functions to work with the data, and we need, for the transformation part or functions part, and for the type, we need types to define the schema for the data. And I imported every one of them. And to open a Spark session, because our first thing we have to do is opening a Spark session, right? This is a Spark session config, and I have this part already written because I can't remember that, so I return somewhere else. Mobility temp. I basically written down all the commands and a few parts of the code that I can't remember here in this notepad. It also includes the SQL files, SQL codes, SQL queries that we are going to use later. And like I said, all the commands that I'm going to run in this project will be given to you in a .txt file, not named as temp.txt, but it will be named in a good way. You can just easily navigate to it. Okay. So I'm going to copy this part, paste it here. So what we're doing here is basically opening a Spark session using Spark session.builder.appName. This will be our app name, traffic streaming lakehouse. You can actually see this app name in the Spark UI. And then we have master of Spark master 7077. We are connecting that to the master, which is this one. We're connecting the Spark session to the master, Spark master with the port 7077. And then config, because we are going to save the data in Delta Lake format, we have to need this package. We have to need this configuration, spark.sql.extension, io.delta.sql delta Spark session extension. We need that. And also spark.catalog.sparkcatalog, org.apache.spark.sql delta catalog.delta. We need these two configurations to be defined in the Spark session builder to make, because we are working with Delta Lake. And also this one as well, enable Hive support. We need that as well. That's it. This is the extra added part, and the rest of it is the basic configurations. The app name, the master definition, and get or create at the end. That we build the Spark session. And then hash. And one more thing. This part of the code is not necessary, but okay, this is not necessary, but when we run this application in CLI, that will generate a lot of records, and that logs will be shown to us in the CLI. To control these logs, we say only show the logs with the severity with the warning or anything more than a warning. Anything other than anything, any logs that are less prioritized than warning should not be displayed, because if we let all of them to display on the CLI, our CLI will get flooded with all those logs. So we control them using this command, this particular line of code. It is not mandatory, but it's a good practice to not overload our CLI. And now raw underscore stream read stream. Now we have to configure Spark to read the stream from Kafka, and that is what we're going to do now. Spark.readStream. We basically use spark.readoff to actually read a file, but here we're not dealing with a static file, we're dealing with a stream. So we say spark.readStream, and format is in Kafka format, and we configure a few options. Because it is running on a port, we have to define the port first, which is Kafka dot bootstrap dot servers, comma Kafka 9092. I'm not sure if I already explained this, but when it comes to these ports, remember we defined 2 ports for Kafka, right? There's a Docker Compose. We defined 2 ports here, right? Here, one is an internal listener and the other one is external listener. So any tool that is connecting to Kafka outside the containers, outside the Docker containers, it should use 29092. Anything inside the Docker containers can be can use 9092 as the listener, and that is why our Python code that generates the data used 29092, because this code is not running inside Docker containers. And here, because we are running this in a Spark, in the Spark container, and Spark container is inside a Docker container, we can access Kafka with this port 9092 because it is running inside. That is an internal listener, and that the other port 29092 is an external listener. That is something related to Docker and Docker composing. Uh, but I just want to, throw that point out there so you can understand it. The next option, option subscribe, and we now subscribe to the Kafka topic that we have our data at. Subscribe, traffic, topic. That is our topic name. Perfect. Another option, starting offset. And this is important when you are dealing with real-time data. Because if you don't configure this option, by default, it takes the starting offset as earliest. And there are three types. The three main types in these starting offsets, one includes earliest, latest, and there is something else. But here, now we're going to define it as latest. But by default, if you don't define this, it takes the starting offset as earliest. What earliest does is, let's take two scenarios here, all right? Now, we're dealing with Kafka and Spark read stream here, right? Now, let's say you have your data in Kafka and you run this .py code, right? And your Kafka has maybe 1, 2, 3, 4, 5 records, for example. And when you run this code, your code read these 3 records. That's it. And Kafka has something called offsets. Whenever you read the data as a consumer, your offset will be saved. Okay, so when you return, it depends on your offset to when you return, the data that you read depends on the offset that you're at. So the offsets are basically starts from 0, 1, 2, 3, 4. It goes like that. So it follows the index numbers. Now, let's take the first scenario. You defined starting offset as latest, which we did here, all right? So when you read these 3 records that are in the topic and you stop this .py code, so you just have those 3 records, right? And now you want to read the rest of the records and you restart this code, rerun this code. What happens is, because the offset is already saved and you chosen latest, it only picks the latest one that are not read before. So when you run the bronze code again, it starts from here and not from the beginning of the topic. That is how this starting offset works. But if you haven't defined this latest at all, and by default it's set to earliest, in this scenario, when you after you read these 3 records and you stop it and run it again, it starts from the first record again. It don't start from it don't continue where you stopped it. It starts from the beginning again, and that creates duplicates. And that is how Kafka works. Kafka and Spark read stream works. You have to be careful with starting offsets. And there are a few other methods to configure it as well. But I remember these are the 2 important ones you have to know about: earliest, latest. I think you got that. Is this capital? Yeah, that is uppercase. Okay. If you have that option configured, and at the end we say load off to load the data. Now, this will read the stream of data that is saved in Kafka from the topic traffic topics through the listener port 9092, which is the internal listener port, and using starting offset as latest. Now that is configured. hash. And these new lines that I'm creating, those are not necessary too. I'm just writing all these things in new lines just for the readability. You can just type this whole thing in one single line and that still works with no difference at all. Just because I'm presenting this code to you, I'm just, typing these codes in new lines, not just because I'm presenting, but even when you revisit this code, it is a lot easier to read the code when it is, you know, uh, typed in the right way. Now, in this part of the code, remember we serialize the data before we send the data to Kafka, because Kafka can only stream bytes. Right here, using value serializer, we serialize the data. What we did here is deserializing the data, because when we read the data, now we have the bytes, the data in bytes, but we need the data in string or a JSON string basically. So what we did here is we say raw stream, JSON stream, JSON underscore stream, a new variable equals raw stream, which already have the data in bytes, dot select expression. We are running an expression on this data and say cast value as string. Now the bytes will be casted into strings and will be assigned to the column raw JSON. Is it a column? Cast value as JSON. Yeah, column. Column raw JSON. that is just our data, and then we are also going to save the timestamp as Kafka timestamp, another column. Basically, what we get out of this is JSON stream will be assigned with a data frame with two columns. One column says raw JSON, and the other column says timestamp of when Kafka received the data, not the event generated timestamp, but the time when Kafka received the data. That is what we are going to save it, because when Kafka streams the data, it streams the data in multiple metadata alongside the actual data, which includes the raw data, timestamp, and the other stuff as well. But we are going to take the raw data, which is our actual data, and the timestamp. That's it. The rest of it, we don't need it. And this timestamp, like I said, that is the time when the record reaches Kafka and not when the record gets generated. So from there, so this creates a data frame with two columns, like I said. To be more precise, so let's say this is the data frame. It creates two columns, like I said, right? It creates two columns. One column is raw JSON. Oh. One column is raw JSON and the other column is Kafka timestamp. Right now, we don't have any schema to our data. So our data is basically saved as a string. So it looks something like this. It says that and says speed as our key and value and so on. So that is it. All the rows, the whole records, the whole record is saved in one single column. Okay, so it doesn't have any schema to it yet. And Kafka timestamp, it has a timestamp. That's a separate thing. So what we are going to do is we're going to create a schema for that data and we assign it. Name it traffic schema equals struct type. This defines the structure of the schema, what to say, the whole record, and then and the flower bracket, and then struct field, and this will define the structure of one single field in that particular record. Struct field and say vehicle ID, which is our first column, and the type of that will be string type. And by the way, when you're defining the schema here using struct type or struct field, when you're assigning a schema, you have to make sure what data types you assign to those columns. When I say that, I don't mean you have to be precise. You also have to think about the fault data that those columns have. Let's say we have speed data here, right? A column named speed, and that supposed to have integer data type data in that column, but it also have fault data. Remember, it also have fault string data. So when we define the schema as speed is integer type, and when we try to assign the schema to that data, it fails because integer also have strings. So we have to make sure the column has the right values to it to assign a data type. Now we're going to copy this whole line again, do the same thing with the next column, which is road ID, which will also be a string type. Okay, and the next column, which is city zone, also a string type, and another column which is speed. Now it should be an integer type, but because it has a fault data, we ingested the fault data, right, using this line right here. It does have a string types as well. So what we do is we just leave the string type to this as well. We later change the data type when we filter or when we clean the data. But for now, this is fine. And the next column, which is congestion level, can be integer type. It doesn't have any fault data in it. And that is why whenever we work with any data, we have to know, we have to read and we have to understand the data that we are working on, so we can actually assign the schema to it in the right way. If we haven't read the data and understand it, we would just assume speed is of integer type and then try to assign it as in the data type as integer, and that causes an error. So that is why we have to understand the data first. The next column is weather, which is also string type, and even time. Right now I leave it as string type because it doesn't have date time type. For Spark SQL types, it doesn't have any date time type, so I'm going to leave it as string type, and later we'll change it to date time when we clean the data. Now we have the schema ready. So we parse the data using parsed equals JSON stream dot with column of data, comma, from JSON of call of raw JSON traffic underscore schema. Now we have parsed it. Before we only have two columns, raw JSON and Kafka timestamp in our data frame. Now we made it three columns. We made it to three columns. We have raw JSON, Kafka timestamp, and a new column as with column is data. We have a new column called data, which has our actual data, but the data under this column, the raw JSON, doesn't have any schema to it, but here under data we have a schema, we have an actual schema to it, but still the whole data is still under one column. Now we have to separate those columns into different columns, right? So we basically flatten that. Flatten equals parsed dot select the first column, which is raw JSON, and then second column Kafka timestamp, and the third column, which is our data. Instead of just having one column for the whole record with the schema, what we're going to do is we split those records, split that record into multiple columns. We can do that using data dot star. So it picks all the columns in that record and then separates them. So if you didn't get the idea behind this, what we did is, so like I said, we had three columns before, right? One is for raw JSON, Kafka timestamp and data, right? This is data and Kafka timestamp, and this is raw JSON. Even when we assign the schema to the data, it is still stored in one single column, the whole data. After we run this, we flatten the whole record into multiple columns. So instead of having only 3 columns, we get multiple columns now. The data column will be gone, but each column in that data, in that record inside data column will be given a separate column to it. So we have speed, vehicle ID, road ID, one column for each of them. Now we actually have a data frame with the data that we defined. Alongside, we have the raw JSON still with us. I still kept it because I need it at the cleaning stage, and also the Kafka timestamp. We will use it. So we have those two still within our data frame. We usually don't keep that. We only keep the data alone. But here we are going to use that in cleaning stage. That's why we kept it. And bronze delta. Right. Now we write the data to bronze delta table. Bronze underscore query equals flattened dot write stream dot format of, because we are going to write the data in delta format, we have to say delta here, and output mode as append. There are a few modes to write the data, which includes overwrite, append. There are a few others. Append basically, what to say, just combines the data. If let's say there is already a set of data that is already saved in that location, append basically combines the new data to the end of that already existing data. That's it. Where overwrite, the mode override basically overwrites the old data with the new data. The old data will not be persisted. And then dot option of checkpoint location basically checkpoint is like an offset. Just like we have offsets in Kafka, here for offsets we say checkpoint locations to track till when we write the data and what we where we have to start writing again. Basically checkpoints, like the name says. And then here the checkpoint location path should be under warehouse, which we what to say, mounted, which is the volume that we mounted to our Spark master when we configured that container, right? Here, to find the path, what we have to do is copy this opt Spark warehouse and use that path. Now we are here, warehouse, and here we create another folder named schk, sorry, chk, not schk, chk checkpoint, and say traffic bronze. So this checkpoint folder, traffic bronze, only have the checkpoints related to traffic bronze application. That is done. And another option, that option is to define the path to save the checkpoints, and this one is to define the path to save the actual data. Basically the same path, but we remove the chk, the checkpoint. That's it, right? Yeah, that's it. And then dot start off to start the writing and save. At the end, spark dot streams dot await any termination. So what this line does is, when we run this application using Python and say this, defining the file name and say Python traffic bronze.py, it runs and it waits for the data. Because it is streaming data, it just waits there. But if we haven't included this line, it just gets the data and stops. So because it is a stream, it should not stop executing. It should wait for the data from the stream to get in, right? And that's why we have this line. So instead of stopping the execution, terminating it, basically, it waits. Wait any termination. It waits until we interrupt the execution and terminate it. Basically, clicking Control plus C until it waits until we terminate it, and then the job stops. That's how it works. Okay, we have the code ready, right? Now, let's open Spark Master here. Spark Master UI, which is, I think, 7077. Is that not the UI? What is the Spark Master UI? Oh, 8080 is the Spark Master UI. So we open Master UI 8080 port, click on that port. It opens the Spark Master UI. Like I said, this is not Spark UI, this is Spark Master's UI. It only shows how many workers are active. You see the worker and the state alive, cores, how many cores that worker has, and how many running applications, completed applications. We haven't run any, we haven't completed any, so there are none. So open this. Now go here. Right now we are in the producer folder, so we have to back up a little bit. So we say cd dot dot. This will go back one folder. So now it is in mobility. Our codes is at okay. Because the volumes are already mounted, we don't run Python and the .py file name. We don't run that command. What we do is we run that through the Docker container. Let me show you. And like I said, I have a command for that. See, I know it is a pretty long command, pretty lengthy command, but that is why I'm going to give you the commands as well that are ready. You can just copy paste those commands. So what this command does is, like I said, this part is already common, right? This part and this one. So docker execute to execute inside the container, and IT is interactive terminal. That stands for interactive terminal, and Spark worker is the container name, which is this one. So we're defining Spark worker as our driver. Whatever we define here, if you have two Spark workers, let's say Spark worker 1, Spark worker 2, and here if you define Spark worker 1 here, that will act as a master and the worker as well. Because now we only have one Spark worker, we say that will be acting as master and worker. So that is Spark worker, and we navigate through Spark submit because we already have a .py PySpark code ready. So we just have to submit it. So we navigate to this file, and then configurations, which includes spark.jars.iv, temp iv. This is configuration to define where to save those external, the packages that we are downloading, right? Because we are going to download a few packages, like I said here, like a package IO delta Spark. Because we are working with delta files here, delta tables, we need to download these packages, okay, these ones. But don't you worry, we only download that once, and for the future executions the same files will be the same files will work. It won't download again. To make sure it won't download again, we have to configure this. So the files will be downloaded at temp.iv, which is VS Code. There you go, Spark IV. This is the location where all our packages will be downloaded. And we said temp IV to refer this inside the container. And outside the container in our PC, the folder represents Spark IV. Here is where the packages will be downloaded. So whenever the packages try to re-download, it checks that particular location. If the packages are exist already, you don't download again. That's how we control it. Okay, that is the package, and then we submit the file by navigating through it. And this is how we submit. The apps folder is referred as opt/spark apps in the container. And that's why we say opt/spark apps / the file name traffic stream jobs.py. Oh no, that is not the name. Okay, I think I changed it. The file name is traffic_bronze.py. So I have to switch the name, traffic.bronze.py. That is the file name. I'm going to change that in the notepad as well, because I am going to give you this text file so you don't get confused. And run it. If our code is correct and everything goes fine, this will execute. And because this is the first time, it downloads the packages. The downloads are not yet begun. Okay, there you go. Now it is downloading the packages. So when you see that message, when you extend this folder, now you'll see all the packages that gets downloaded. We need all these packages when we work with Delta tables. So these are all the packages, catch and jars. Like I said, it only downloads once. One package will be downloaded once, and later it will be referred to that. Okay, we did got an error. And the error is no module named PySpark.sql.function. And I can see the error here itself, because it should supposed to be PySpark.sql.functions and not function. S is what missing here. I do this error all the time. So S is what missing here. Now I fixed it, and so I run the same command again. Run the same command, copy that. That was literally the third line of the code, and I committed an error. I hope I don't have any errors again. There are no errors, I think. Okay, if there are no errors and the code is running, to confirm the code is running, you can extend the warehouse section here. If you see these two folders, this is for the checkpoints folder, and this is the folder that the data is actually stored at. All right. Now, I really think it did not took any data in yet, because it is set to latest and not earliest. And that is why it never took the data, because the data is old. So we have to generate the data again. So let's do that. Open a new PowerShell. I'm going to keep the stream in the background, by the way. This is still running. We haven't terminated that yet. Here, cd mobility / producer. These where our producer code is. Copy the name. python.py. Run this. Now the fresh data is getting streamed in Kafka. You can see the files getting generated, right? That is the confirmation. If you only see 2 files, in that 2 files, even the 2 files is not 2 files. Basically, when we save the data in Delta format, it creates 2 files. A JSON file, which is the actual data, and a CRC file, which is like a security for that file to make sure the data is not corrupted. So CRC files, so you see the .crc at the end, these are the CRC files, and these are the Parquet files, not JSON. The data is stored in Parquet file, Parquet format. .parquet this is the real data. Okay, we have all the files. I think we have enough files. Now I'm gonna stop the stream. Yeah. Now stop the stream. This one, using Control C. That will stop the stream. Okay, we have the data here in the traffic branch. If you have enough computational power, and if you're doing the project faster, you can just keep the stream running, like I said, so you get more data to work on. But now I have to present, I have to explain, so I can't do that. This is still running. If you open Spark Master UI, refresh, now you can see there is one running application, and the name is Traffic Streaming Lakehouse. Remember when we named our application in our code? Traffic Streaming Lakehouse. That is the name. We can identify the job, Traffic Streaming Lakehouse. That is the application that is still running, and the resources are allocated to it. So when the resources are allocated to this, if we try to run another application parallel to it, it won't run because it waits for the resources, because we only defined one single worker. So we only have one worker which can only execute one application at a time. So if you run another application, it waits for the resource. So only after this application is terminated or done, that will be executed. Now, so make sure. So if you want the parallel processing, I would recommend to create 2 more workers. So you have 3 workers in total. So you can run bronze, silver, and gold applications at the same time parallelly. And you have 1 worker assigned to each of them. Okay, now let's hit Control+C. This will stop the execution, which means this application will go to completed application and the resources will be still available. Right here you can see, right now the 2 cores are used for this application. When we refresh, 0 cores are used in this worker. So this worker is now ready to work on a different application. Okay, we're done with one transformation. So we're done until this part. We're done with source, Kafka, and bronze stage. We are heading to the cleaning stage, the silver data stage. And by the way, we are storing the data, our data in Delta table format, right? Delta Lake. To confirm we are actually storing that in Delta Lake, Delta, whatever the data that you store in Delta format, it creates a separate folder named delta_log. That is a confirmation your data is actually stored as Delta Lake. Right here in our bronze, there is a folder that is created delta_log. There you go. Now that is the confirmation. So there are a lot of perks of storing data in Delta, which offers features like ACID transactions and time travel, if you know, which includes we can run back in time and go to the previous state of the data that we had. If you go through a Spark masterclass, I mean not Spark, not Spark, SQL masterclass, you would already know about version. No, what did it say? Time travel. Not even Spark. Spark. Go check out Snowflake if you don't know about it before. If you haven't heard about it before, go check out Snowflake, where I explained how the time travel works, and I also demonstrated how it works in Snowflake. So that is how time travel works. We can just go back in time and go to the previous state of the data. Now we're done with that. Let's head to the next stage. Now we're heading to the silver transformation. So before actually typing in the code, what I usually do is I actually write all the columns that we have till now and then the errors that we have to deal with in a notepad. So first I'm going to type in all the columns that we have till now, which includes what do we have? We have raw JSON, right? We have raw JSON in our data frame. Raw JSON, and we have Kafka timestamp. We don't have data, but we have the rest of the columns, which include vehicle ID. So we have to type these columns in, or else we get lost. So we have to keep track on the columns that we have in our data frame. That is a best practice. We have city zone, speed, and then congestion level, weather, event time. So these are the columns that we have till now in our data frame, which are basically these two are not included in the actual data, but these are included. And I'm going to join them anyway. And the errors that I ingested that we have to take care of. Spelled errors wrong. Okay. And the errors include all of these. These are all the errors. Well, we want these column names to keep track of the columns that we're working with, but we need these errors as a checklist. I don't actually have this. I don't usually list these errors because when we work with the real data, we don't actually know what errors that data comes with, right? Because this is a simulation, I know what errors that data has. But in real world, we can actually keep track of columns, but not errors. But here, just to explain, so this is a cleaning stage of the data. This is where we start cleaning the data, right? So we check these lists and see what errors we cleaned. That is why I created this. Now we have that. Okay, now we create a new file named traffic silver.py. And we need the same stuff that we used before, which includes these and the Spark session builder, this, but we have to change the application name, but so we can't have the same application name twice. We change that. You know what? Just gonna change traffic silver layer. That's perfect. Anything else? No, that's it. We have that. That'll build the Spark session for us. And also the next one, the logs one, we need this one too. Okay. Now we need to read the bronze stream. And we name the data frame as bronze df because we're getting the data directly from the bronze layer. Spark.read stream dot format of delta, because we are reading the data. The data is in delta format. And dot load of. This time it is easy because we can just copy the write path of bronze for the read path of silver. Like that, with the double quotes. That's it. Now the next step, we're going to flag a few columns, a few rows. So we flag them now, and then we filter them, filter the rows that has the fall data later with these flags. So let's do that. Till now, we haven't changed anything in the structure. We have the same columns. But now we say DQ, DF, data quality of the data frame, DQ, data quality, DF, data frame. From bronze DF dot with column of DQ, DF, comma, when column of vehicle ID is null, say missing vehicle, then dot when of call of event time dot is null, missing time, then when call raw JSON dot contains corrupted comma corrupt JSON. Otherwise, say OK. Okay. Now we're creating a new column named DQ. DQ flag, not DQDF. That's the data frame name. Now this is a column name, DQ flag. So because we are keeping track of all the columns, we're going to keep track of this as well. We just added DQ flag. With that column, we just flag all the rows that has either vehicle ID as null or event time as null, or raw JSON, which is this column, which has just a raw JSON strings. If that contains the string corrupted, remember in one of our errors, we ingested this as our record, corrupted event. So it checks for corrupted in the text. This has corrupted in the text. So that will be flagged as corrupted JSON. So we just flag them now. Later we filter all these flags out. So if the row has none of these errors, say OK as a flag. Now we just flagged, right? Next. But before filtering of the data, we're going to add a few more flags and filter out at once. We use DQ df dot with column of speed int. Remember, we still have the data type for speed as string. So we are going to create a new column as speed int and call of speed cast it to integer. Now this will work if the data has any strings in it, unlike the other the structured schema that we defined. Here, if the data has any strings, that will be taken as null values, and only the integers will be considered as the actual values. With column event ts, and also the event timestamp of event time. Also this one we defined as a string in our data types in bronze, right? String type. So we create a new column called event ts and cast it to timestamp. Now we have two more columns added to our data, which is speed int and event ts. And then business validation rules. Validated equals typed, which is our data frame, with column of speed int is greater than or equals to 0 and call speed int less than or equals to 160, comma 1. I think I messed up. This is squared, this is squared. No, I did not. I'm just counting the parentheses that are left. Okay. Otherwise, dot 0. With column time valid when of call of event timestamp is less than or equal to current timestamp of plus expr expression of interval 10 minutes, comma 1 and the parenthesis dot otherwise of 0 and we have a parenthesis here. Okay. Now we are adding two more flags. One is for valid speed and the other one for time valid. So two more columns. So to make sure we take out the invalid speeds which we have in our errors, which has negative speed, extreme speed, right? So we have to deal with that. So we create a new column named speed valid, and when column of speed int is greater than 0, greater than or equal to 0, and column of speed int less than or equal to 160, that is the valid speed. Assign it with 1, otherwise with 0. So 1 is valid and 0 is not valid. So it should be, the speed should be anywhere between 0 to 160. If it is over 160 or if it is less than 0, it is invalid speed. So we're dealing with these two errors with that flag. And the next flag is time valid, the same, almost the same logic. When column of event ts is less than current timestamp, the time right now, plus expression interval 10 minutes, So it should not be the future time. So it checks if it is less than or equal to current timestamp plus expression interval 10 minutes. So it adds 10 more minutes to the current timestamp and checks if it is less than or equal to that. Only then it is valid. So it is 1, otherwise 0. So that flag will deal with future event. Okay, so with that we are adding 2 more columns, right? So I have to track them as well. Speed valid and time valid. And the next one. Now we have enough filters. Now we're going to filter them out. Enough flags. Now we filter the data out with those flags. Good records. Clean stream equals validated.filter of column of DQ flag, which is our column we created for flagging. DQ flag equals okay, and column of speed valid equals 1, and column of time valid equals 1. Now this will filter out most of the errors that we ingested before, which includes missing vehicle ID, which is this one. So I'm going to check the errors that we deal with. All right. So for the checked ones, I'm gonna use C as the symbol, capital C. Yeah, capital C at the end. So we haven't dealt with the null speed, negative speed, C, and extreme speed, C, because right here we only filtering the speed valid equals 1, and the 1 is only assigned to the speed int with in the range of 0 and 160. So we're dealing with these two, negative speed and extreme speed. And we're also dealing with what else? Time valid, which is future event. We're dealing with the future event as well. And then, is that the future event? Yeah. What else are we dealing with? Speed is done, and the DQ flag right here. So we're dealing with the null vehicle IDs, which is where is it? Oh, we don't have any null vehicle IDs. Okay. Do we? No. Okay. Well, we don't have any. We haven't inserted, but I'm going to leave the code as is. But in case, just to replicate the real world cleaning, I'm going to say take the null values out. but we haven't ingested that error, but that's fine. Late event corrupt JSON, and we are also dealing with the corrupt JSON. So this is done. Okay. Moving on. Handle late data. That is one of our error. We handle it using watermarking. Watermarked equals clean stream dot with watermark of event ts comma 15 minutes. So what this does is, only if the data is fresh, it doesn't the event generated time doesn't pass 15 minutes from the current time, only then that will be accepted, the rest will be taken out. So with that we're dealing with the late event as well. So this is done. This is done. Moving on. Deduplication. Deduped equals watermarked dot drop duplicates of vehicle ID comma event ts. With that, we're dropping the duplicates, which has same vehicle ID and even timestamp. So this is resolved. Duplicate vehicle ID. Did we create any new columns? No, not yet. Okay. What else do we have? Oh, we also dealt with the wrong data types because we created a new column which is speed int, where we speed int and event ts, where we actually define the assign the actual correct data types. So we deal with that as well. Now we have null speed, which basically we don't have to, but if you want to, you can just fill the null values of speed with the average speed or something like that. But if you leave it, it doesn't cause any problem as far as I know. So I'm gonna leave that error, and also schema drift. If you don't care about that column, we don't need to clean it, right? We don't have to clean that column. Even the schema is drifted, that doesn't, wait. Yeah, that doesn't even have any column because we haven't included that in the schema, right? In the bronze, we haven't included that new column, that error column in here in the schema. So it is not even considered as a column in our data. So it is not here in the columns. So this is also taken care of. There's only one thing, null speed should be taken care. But like I said, if you want to, you can just fill those null values using fillna. I mean, not fillna, that is pandas. Using functions, and you can fill those null values as well, but I'm gonna leave them. This is fine. This is just fine. Now I'm gonna do a little bit of feature engineering. Not too much though. Say silver final. This will be the final finalized data frame. I'm gonna add a few more columns. Deduped. With column of hover, comma, hover of event ds dot with column of peak flag, comma, then of column of hover dot between of 8 comma 11 or column of hover dot between 17 comma 20. One, otherwise 0. And one more with column speed band when column of speed int is less than 30 comma as low dot when of column of speed int less than 70 comma medium otherwise high. With that, we created 3 more columns. Right? We created hour, which just separates hours from the whole timestamp. So just a separate column for hours. If you want to create a file, create a dashboard or create a chat in the dashboard, which shows hourly congestion level in a particular area, you can use that hour. And then with column peak flag. So peak flag shows the hours with peak traffic. What are the usual hours with peak traffic? 8 to 11 or 17 to 20. 17 to 20, which is 5 o'clock to 20, or 5 o'clock to 8. So basically, the 5 o'clock is where usually the employees get free after their jobs. So these will be the peak hours. So that says peak flag as another column, and speed band. So we named the speed bands as less than 30 is low speed and greater than 70 is medium speed. Sorry, less than 30 is low speed and less than 70 is medium speed, and anything other than that is high speed. We have that column as well. That's it. With that, our silver is ready, silver data frame. Now we write that to our silver table. Output mode, obviously append. You know what? I'm going to copy paste this from our bronze. I think I'm here, right? Yep. Checkpoint, and this should be switched, the location. As traffic silver. This one is traffic silver 2. Traffic silver. Perfect. And the last line as well. Copy that from bronze. Perfect. Now we have this silver transformation code ready as well. I hope we don't have any errors. So let's run that and see. I spelled it wrong. Silver traffic silver .py. Perfect. Traffic silver.py. Run it. I'm 90% sure I will face an error. Now extend the warehouse again and check for, okay, there you go. There is an error. It says right here with column. Unable to load native Hadoop library from your platform using built-in Java classes where applicable. Dot with column peak flag. Where is it? Peak flag, I think it is at the end right here, right? Yep. What is with this code? I just checked it out and it says the issue is with the syntax and not the code itself. So it is the indentation error. So what I'm going to do is, the code is correct, but the way I formatted it is not correct. And now we split the code. Okay, we have this. I'm gonna give it a break right here. Say, first I'm gonna open a parenthesis and give a break right here, and another one right here, and another one right here. They shouldn't be here. So the indentation is nothing but the space that we give between the lines. So when I write this when in the same with the same indentation as with column, Python thinks this is a new statement and not part of this with column statement. So you have to take care of these tab spaces. Now this is inside this statement and not a new statement. That is how it works. Same thing with every one of them. And otherwise, and here starts another column, another statement, and that's how it goes. And indentation right here, and another one right here, and we can give it like that. And we end everything with another parenthesis. Perfect. We can give one more right here, just for the readability. We got everything correct. Now let's run that again. We got one more error. What is it? Call our right here. So this should be comma. All right. I guess that's it. Run that again. I hope we don't get any errors. Yep, that is running. Now we should be able to see another folder created here named traffic underscore silver. Now we got another error. What is it now? When of missing one required positional argument value. Where is it? Between, dot between, and okay, it is with the indentation again. I'm gonna leave it there. Let's run that again. I hope that fixes everything. Again? Okay. Oh, the same error. All right. We got the same error. This is just a simple syntax errors. The way I placed the parentheses is not correct. So Python thinks I excluded otherwise here. So it should be included. It has that. This has. Okay. Perfect. Now this should work. Hopefully. This is like the third or fourth time that I'm trying to fix the error. The worst part is these errors are not even the actual code errors. These are syntax errors. The way I ignored the indentation and parenthesis, the placement of parenthesis. There you go. Now we have this folder which got created. Silver, traffic silver. All the data is getting loaded to it, but it's not done yet because this file delta underscore log should be created. Now it is created. Now it is. Now I think it is done. That's fine. I'm gonna keep it running in the background. So with that, we're done with the silver stage, the cleaning data stage. This one. Now we head to gold, business ready, making the data business ready. We are going to implement star schema here, and I'm going to talk more about it. Now, talking about the goal layer, we're going to make the data business ready, right? So I'm going to implement star schema in this. And for the people who never heard of star schema is us basically splitting the table or the data into multiple tables. Instead of having one single table for all the data, we split the data in that table to multiple tables. So there can be multiple dimension tables, which represents uh, a few dimensions of data. And then there is one fact table for all the dimension tables that connects all the dimension tables together. I think you got it. So, for instance, you know what? I'm going to create a new file, traffic gold.py. Okay. Now, let's say you create 3 separate tables. And each of the table represents separate individual set of data. Now, these tables are considered as dimension tables, and there is one table that connects all these tables together, which will be called as fact table. So these are dimension tables, and this is fact table. They will all of them will be connected to one single common table, that is fact table. And this relation will also be taken implemented in Power BI as well. When we import the data into Power BI, this relation can be implemented too. I will show how we can connect these tables together in Power BI later, but this is how star schema works. Instead of one big table with huge amount of data, we split the data to multiple tables and connect that using one fact table, one common fact table. Now, for the goal transformation, yeah, obviously we need these libraries, but we don't need the data types for this. We just need these two. We need the function one and the session builder. And then also this one, this whole thing. And we change the app name. Perfect. And also the next line, which is Spark context. Now we read the stream. We read the data stream. From silver table. Silver stream equals spark dot read stream dot format. The format is delta format and dot load of, and the path is the same path that we wrote the data in the silver transformation. Same path. We read the data from that. We read the stream from that. Now we create our first dimension table. Dimension for zone. You can become quite creative with creating these dimension and fact tables, because this determines how and what parameters you use in your final dashboard and charts when you create them. So you can be creative, but for me, I'm going to create a dimension table for zone, the city zones. DIMZONE dimension zone equals silver stream dot select of. I'm going to select the city zone column. Well, obviously we have a lot of columns. We don't need this checklist anymore. Take that out. We have all these columns in our data frame still, right? Now we're going to use city zone column. Dot drop duplicates of dot with column. Yep, that's correct. Zone type. When of call of city zone. Forgot the codes. CBD. Keep forgetting the full form of it. Central Business District, CBD. Commercial dot when of call of city zone is equals to tech 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 park IT hub dot when of call city zone, this time dot eason airport, comma train station transit hub dot otherwise. I have to be careful with the parentheses. That give me a lot of trouble for the last transformation. So residential. So what I'm doing, no, it's not done yet. I'll do one more thing. Dot with column of traffic risk when of call of city zone dot is in CBD airport. That should be high. Dot when of column of city zone is equals to IT hub. IT hub. Wait, not the IT hub. I have to say tech park. Okay. Tech park. Medium. Otherwise low. That's it. Now, what I did here is from the silver stream, I only picked city zone, and I created a couple of columns. Before creating the columns, I took out the duplicates. I dropped all the duplicates because we only have how many? City zones. We have like 5 city zones, right? And they'll be repeated throughout the records. And we don't, for this dimension, I don't want the repeated, the duplicates. So I took only the unique ones out. So there will be 5 records in this dimension table because I went for drop duplicates. So this dimension table only has 5 records. And I created a couple of new columns, which includes zone type when column of city zone equals CBD. Then the zone type should be commercial. When the city zone equals tech park, it should be IT hub. When the city zone equals is in airport or train station, that should be called as transit hub. Just to make it, just to cluster the related city zones together. So I created a new column called zone type. Like I said, you can be creative with this. Okay, and then if there is nothing matched, otherwise residential zone type dot with column, another column, traffic risk. When column of city zone is in CBD or airport, high. And also train station, right? The train station should also be included here because train station will also be the high risk of traffic areas. City zone is in CBD, airport, and train station. The traffic risk will be high. When city zone is in tech park, medium, otherwise low. So this table has this table will be having 3 columns and 5 records, and each record has city zone, zone type, and traffic risk. That is our first dimension table. Now write this dimension table into our Delta Lake. Zone query equals dimension zone dot write stream. I'm gonna copy paste this part. I already did that, so copy paste this part. Delta output append checkpoint should be different, should say dim zone. The same thing with this, copy that, whereas dim zone. Perfect, that is done. Now the next dimension, moving on to the next dimension table. Dimension, this table is dedicated to the road. Dimension road equals silver stream dot select of, we are going to select road ID from this table, nothing else, just the road ID. I created all these columns, but if you think any of the columns are useful for your dashboard, you just include them in the fact table. Or if you want to do any type of aggregations or any extra columns or any new calculations, you can actually create a new dimension table and then do that in that dimension table. Because at the end, we will connect the fact table with the dimension tables, right? So yeah. Road ID. Obviously drop duplicates, because I think this has 4 types. So this dimension table creates only 4 records. Drop duplicates of dot with column road type when of call of road ID dot ease in of, I'm going to select a random 2 random road IDs, or 100 or 200, and assign highway to the road type. Otherwise of city road, and another column speed limit when of call of road ID is in, or 100 comma or 200, can be 100 because that's a highway, but otherwise if it's a normal road or a city road, should be 60, should be the speed limit. Same thing. This dimension table will have 3 columns and 4 records, which includes road ID, road type, and speed limit. For the road type, if I just selected 2 random road IDs with R100 and R200 and assigned the road type as highway to it, and otherwise, which means the rest of the road IDs, road R300 and R400 will be assigned as city roads. And the next column, speed limit, when column of road ID is in R100 or 200, which are highways, the speed limit will be 100, but in city roads, the speed limit will be 60. That's how this dimension table works. We're done with the dimension tables. No, not yet. Sorry. We have to write this dimension table into our Delta Lake. I'm going to name it road query. Delta and dimension road. Same for this. Dimension road. Anything else? That's it. Now we head to the fact table. I'm going to just select all the columns that I need from this rest of the columns. Not rest. We should also include road ID and CT zone because I have to connect this fact table with those dimension tables in Power BI. So we have to include that columns as well. Okay, we have that. Fact stream equals silver stream dot select of vehicle ID and road ID, city zone, let's say speed int. I'm going to ignore the other speed, which is this one. That is defined as string. So I'm going to ignore that. I'm just going to use speed int here, and then congestion level event ts. We only need event ts because this has the right timestamp data type. The other one, which is event time, is assigned as string. So we need this one. That's it. I'll also take peak flag with me and also speed band that I created, and also just the hour, just in case if we need it, but I'm not going to use it. Maybe mostly I'm not going to use it in the dashboard. Weather. I think that's it. I select most of the other columns that I want in my dashboard. The rest of them are ignored. Like these speed valid and time valid, they are flags. We don't need them. We just wanted them for filtering, so we don't need them. And event is included, speed int included. This flag is not included. Weather is not included because that is a string. Now event time is not included. Weather is included. Yeah, weather is included, and speed, city zone. I think that's it. That's it with the fact table. Maybe we add another column. I'm not sure if I don't even use this, but I'm just going to add it anyway. Fact enriched. One more column. Fact stream with column of date, because just because I created a column for hour, I'm just going to create another column for date alone, just the date, not the time. Event yes. Well, I can't use these columns now because all the date, all the event time in my data will be generated in the same timestamp because I just generated now. So the date will be useless because it only takes, all the records has one date, one single date. So I can't create a time line chart, right? Congestion to time line chart or something like that, because I only have one date that is assigned to all the events, because I only ran the the producer code today. If you want diverse data with diverse event times, you can run the producer code today and tomorrow and like 3 or 4 days, not continuously though. Just you can just run it and leave it, something like that, and add those extra dates, so you can just create a line chart. Okay, we have that, and that's it. That is it. I'm just going to write the stream now and say fact query, and this should be fact traffic. The same thing for this, fact traffic, and start, and at the end we have to include this. Remember, we have to do that line as well. Save. With that, we have our goal transformation code ready. We just have to implement it, execute it. So let's execute it. Now let's stop this silver job that is running, Control C, and execute the gold one right here. The job name is not correct. It should be traffic gold. Perfect. Run it. This should create 3 separate folders, 2 for dimensions and 1 for fact. Okay, we did got an error. What does it say? Column of takes 1 positional argument, but 2 were given. Okay. Where is it? City zone. Okay. Right here. Oh, it's a parenthesis again. I think I added an extra parenthesis here. Does that fix anything? I think I have to take this parenthesis out then. That'll fix. Maybe. Maybe that'll fix. Run again. I forgot to change the name. Should be gold, traffic gold. Traffic gold.py. Okay, run that. With column. I'm 100% sure that is something to do with the parentheses here. Right here. I have to count all the parentheses and take care of them. Definitely a syntax issue. Let me separate all of them and see. So this one starts at here, ends at here. Everything seems perfect. I don't know what's happening. I'm gonna run that again. Okay, I think that is fixed. So that is with this parenthesis. Okay, that is fixed. Now the problem is with the road ID right here. It says column type error. So here I typed in other, it should be otherwise. Otherwise. I think now it works. And other error, I think that is fixed, but this is a different one. But what is it? So it clearly says, the error clearly says, a column or a function parameter with a name. You see that? I spelled event ts wrong somewhere. So it should be right here. This is a typo. Now I corrected it, event ts. Perfect. Run that again. This should create 3 folders, like I said. One each for the 2 dimensions and one for the fact table. There you go. The fact table is created now, fact traffic. And we're still waiting for the dimension tables. There you go. The first one, dimension zone, is created. We still need dimension road. And there goes the dimension road. Now we have all the data. Now we have all the tables from the gold, which means we're done with the goal layer. This one. Now our next step is to set the Hive Meta store. We just have the data stored in the Delta Lake, the Delta storage, Delta Lake storage. But in order to connect to Power BI, we have to create tables in Hive Metastore. Like I said, Hive Metastore doesn't actually store the data by itself. It only stores the metadata, which means it stores the table name and the path to find the data for that table, and whatever the views that we create. So what we're going to do is we create tables that points to the fact and dimension delta tables location, and then we create views for all of them, because for some reason those tables cannot be accessed directly. in Power BI. We have to create those tables, and then we have to create views for all those tables. And then we connect to Power BI and select the views, and then import those views into Power BI to create the dashboard. That's how the flow goes. Now let's talk about that. Now we're almost done with the whole project. We only have 2 more final stages to take care of, which includes establishing a Hive Meta store and then establishing a thrift server for that Hive Meta store so we can connect Power BI to our data that we stored. This stage includes uh, more commands than I used till now and a few more queries to create tables and views for the data. So head to the PowerShell. The first command will be now we run this command to execute our bash commands inside the Spark worker container. Now whatever we do here will reflect into the Spark worker containers directories. Beginning with, we create a directory where our Hive metastore can actually store the table data. When I say table data, I don't mean the actual data that the table stores, but like I said, the table's metadata will be stored in that location. So say mkdir /tem/spark hyphen warehouse, and we are creating this folder, and next we're going to assign this as our location to store the metadata of all the tables that we create. Then we run after creating the folder for the database to store the data, the metadata, we then give permissions for reading, writing, and modifying it basically to the metastore using this command. Now the next command is us actually establishing a connection to Spark SQL on Hive Metastore SQL database. To establish that connection, I have a command which is a lengthier command which I cannot type in manually. It is right here. I'm going to copy paste this and run it. Now we are actually connected to metadata database, Hive Metastore database basically. Here, now we create a database and create a few tables, not few, 3 tables, one for each data, 2 for dimensions and 1 for fact. First to create database, mobility, now after creating the database, we have to switch to that database. So whatever we work after, or whatever we create after that will be reflected to that database, not a default one. Right now it is a default. So we switch to the database that we created, the mobility one. So we run use mobility. Now here we create a table for fact traffic, and what else do we have? Dimension road and dimension zone. First, for fact traffic, create table fact underscore traffic. Enter. You can actually click enter before even before the query is ended, because this is SQL, and any transaction in SQL only ends when you type a semicolon at the end. That is how you say SQL. So this is the end of my query. So because I haven't typed any semicolon in that query, the query is not ended yet. It is still going. So using delta, and we define the location of the data, which is basically opt spark opt slash spark slash warehouse slash, and this one, fact traffic. This is the location that we stored our data, right? Traffic, quote, and the semicolon. There ends the transaction. Now this will create a table named fact traffic using delta. If you just connected to SQL database directly using delta, this part of the query will not execute. Because we connected to the database with this long command that we typed in, which includes a lot of packages. All these configurations, we first define that, you know what, let me explain the command that we ran before. This is the command, right? So here's the location where these inside the container. We navigate to Spark SQL, so we can actually create an SQL connection and write SQL queries in it. And then packages include io.delta.delta Spark, because we are using Delta Spark in this data. And because we are referring to that Delta table, we have to define this package. This will be downloaded and saved at. We have to configure a location to save these packages. Remember, before we used .ivy. We use the same location to save these packages as well. So all of those packages will be saved at one particular spot, which is Spark IVY. This one right here. And then all of these have packages and configurations to let say the Hive Meta store to actually create the tables and get the data from the Delta tables, then establish a connection and all of that. So these are all very important. And this one at the end is us defining the connection between the directory that we created before for the database alone to save the metadata of our tables. So we mount that at the end right here. That is how we establish the connection. That is the only reason this query runs with no errors. Even it has using delta, which basically cannot be executed in a normal SQL, but here we can. When we run it, if you don't see any errors, warnings are fine, but errors are the one we have to take care of. We don't see any errors here, so I think this is executed. Just to make sure, we can just run a query saying select count of asterisk, which represents all, count all from table. The table name is fact traffic. Run it. And there you go. It has 5 records stored in fact traffic. Now let's create tables for the rest of the 2 other delta tables too. And you might wonder, here we are creating a table, which means you might think these are regular SQL tables which has static data stored in the table, because basically table stores the data physically, so that is static. But here we are creating a table that actually updates automatically by itself, because we are referring the data for this table from the location where we store the delta table. And that is why, because if we create a static table, there is no point of us calling this project a real-time project, because we have to run these queries over and over again to refresh these tables. But here, we are referring to the delta table that we already created. So whenever the data in the delta table changes, the data here in this table will reflect those changes as well. Let's go ahead and create another 2 tables for the other 2 dimension tables. dim underscore zone using delta location, the location of dimension zone, and run it. Make sure that is created. Running the same query by copying this name. That prints 5, obviously. Yeah. The next table, create table, dimension road, using delta and location as that, and a semicolon at the end to end the transaction. Perfect. And we check the table again. I can already say this table only can have 4 records because we created that. So it has 5 records. Okay. I'm not sure how it got 5 records in it. So we have train station, transit, hub. Something went wrong. Well, everything that we did here is correct, but somehow all the tables that I created got the same data. See that? So that the dimension road has the same data, which should be the zone data, dimension zone data, and dimension zone has the dimension zone data, and fact traffic also have the dimension zone data. And the part that I messed up is not here. Way before this, when we worked with the goal transformation, remember we just copied and pasted the right stream for all the 3 tables, and then I forgot to change this, the name of the data frame that we're writing to the stream. That is what made all the data to have all the tables to have the same data. So to fix this, I first changed this goal transformation code from by just replacing these data frame names first. And here, fact enriched. Now the code is fixed, but the data is already written. So we delete the data. So we delete fact traffic, dimension zone, dimension road, and we also have to delete the checkpoints, dimension road. Now I'm going to use this and run this goal transformation code again. Hopefully everything gets fixed. Okay, that didn't work. So I'm going to run from the beginning again, from bronze, silver, and gold. And yeah, I'll pause the recording for now and I resume it after I've done that again. Now I did fix everything and I make sure everything is all right. Right here. Okay, so when I select everything from dimension road, I can see 4 columns with R100, 200, 300, 400. The same way, when I select everything from dimension zone, we have 5 rows in total. 4 rows for dimension road, and for dimension zone, we have 5 rows. And for fact traffic is basically a large table, so I haven't printed all of it. I just printed count of all from fact traffic, and I got 31 records. So that is a minute error that I made in the goal transformation that caused me to run the whole transformations again from the beginning. Now that is what we have to keep in mind when we copy paste something in a code. We have to make sure we modify that part according to where we paste it. Now we're done with that. And like I said, these tables cannot be referred in Power BI directly. We have to create views for every one of these tables again. And then we refer to those views so we can get the data to Power BI. So to create a view, I'm going to start with the fact traffic. As so I have a query for this view. This is not a regular query. We're not going to just map those columns and create the view. Instead, we're going to do a final check to make sure every single column has its appropriate data type assigned to it. And that's why if it is in a wrong data type, we are going to cast it to the right one. If it is right, it won't be changed anyway. So this is the part that I'm going to use. Here, we're casting every single column. Vehicle ID as string, road ID string, city zone string, and speed int is double. City road ID is string, sorry, congestion level as int, event timestamp as timestamp. And also, yeah, I think congestion is still as string. We haven't converted congestion level to int, but we have to convert it because if it is still in the string, when we connect to Power BI, we cannot actually do any arithmetic operations on that column because that is of string type. It should be integer type to integer or double type to let us do mathematical operations on that column. So we have that. Run it. That view is created. We do the same with the other two views. City zone as strings, zone type as string, and traffic risk as string too. Well, for these two views, we don't have to because we created most of this tables data. So we don't have to basically do the casting, but still this is the last chance we can actually cast the data types. So to make sure everything is assigned in the right way, this is the final check. Like that, we have our three views created. So the next step will be, after creating all the three views, we have to download a few jar files because the last one will be establishing a thrift server which that is connected to the meta store database. Then we connect this thrift server to Power BI. So for that, we have to change the directory first. First, we have to exit this Spark SQL connection. So we type exit, a semicolon at the end to exit the connection. Here we type cd opt spark jars. Now we change the directory where we download these files, both of them. And like I said, again, I will be giving all these commands in one single text file, which will be available in the GitHub repository, which repository link I will be pasting in this video's link description. After that, we run this command. This command has the same. It has all the all the packages that we need to download and the configurations to establish a thrift server for a meta store, Hive Meta store. Paste it here, run it. This, yep. When you see this line printed and no errors shown, that is a confirmation that this Hive server is established successfully. After establishing this, now we're done with this part as well, which is Hive Metastore, establishing a Hive Metastore metadata database. Now we're done with this. We're going to Power BI. We have to connect Power BI to that data using the views that we created and then pull the data into Power BI. Then we create a dashboard. So let's do that. So connecting Power BI to this data is simple. And to do that, we open Power BI. Well, most of the people know what Power BI is. When you're in data, you already know. You at least work with Power BI once in a while, right? But for the people who don't know, you can get this app from Microsoft Store or even any browser. It is free. And I will also leave a link for this app as well in the description if in case you can find it. There's no way you can find this, but just in case. So here, I forgot to say what to do. Okay. This is the home page. We click on get data from another source. Click on it. And in search, we search for Spark. And here we click on Spark, connect. For the server, we have to use the server that we defined in the Docker Compose for the Spark worker, this server, because that is where we establish the thrift server. So we use this 10,000 as our port to connect Power BI. So we say localhost colon and 10,000. And for the protocol, we have to pick standard, not HTTP. And then because this is a real-time project, the data changes with time. So the dashboard should also be changed, adapted accordingly with the data changes. So we have to pick direct query, not import. Import basically imports all the data, and the data you have in the Power BI will be static and cannot be changed. Whereas direct query, whenever you do any operations with the data, it goes back to the data source and then gets the data from there. So the data will be fresh. So that basically real time. So we have to pick direct query here and click on OK. Well, you have to choose direct query, but I am going to pick import. I have reason for that too, because I want to give the Power BI file to you guys. So if I pick direct query, I may not be able to. I can actually give you the file. That file might not work. It might fail. So I'm going to use import and then create the dashboard so I can give you the Power BI file. I got a lot of requests from people asking for the Power BI file that I create the dashboard in. So I'm going to choose import here and then click OK. But you chose direct query. OK. Here's the thing. After clicking OK, it asks for the credentials, login and password. Because I already done it before, Power BI saved those credentials. So the credentials can be anything. You just type any credentials, a random text or characters in that username and password, it still takes. I typed in Spark in username and password. So you just type Spark in username and password and select proceed, and this will be the page you will be landing on. From here, we pick the views that we created, not the tables. Even if you try to pick the tables, you can't access them. Like I said, it blocks. See that? The table has no visible columns and cannot be queried. So that is not possible, but the views can be queried. All of them. There you go. And this one. They can be queried. Select all the 3 views that we created and click on load. Now that will import all the views into the data pane right here. Let me see if I can zoom this. Oh, I cannot zoom the options. Okay, maybe not. Okay, here we have all the data here. Just I'm going to double check if the data is actually working. Yeah, it is working. Yep, perfect. Now you have all the views here, but like I said, these tables belongs to a star schema. So the 2-dimension tables should be connected to the fact table, which will be the common table. So to establish the connection in the Power BI, we can head to the model view right here in the left pane. Click on model view. Oh, mine is automatically created somehow. Well, Power BI, a few times Power BI automatically creates the connection between the tables when it sees the common columns in those tables. Like as in this one, we have city zone and city zone in fact table as well, so it connected automatically. But I'm going to take these connections out and show you how to connect them manually if Power BI doesn't pick them up automatically. Okay, so from dimension table, you click and hold the city zone, drag it, and drop it on the city zone in the fact table, and this menu pops up. Here, you check all the details, all the table data that is getting connected, and the cardinality should be 1 to many. Dimension table should be 1 and the fact table should be many, because dimension table doesn't have any duplicates for city zone, right? We deduplicated it, so it should be 1 to many relationship here. So this should be the cardinality, and save it. Same thing with the other dimension table. Here we have road ID, drag and drop the road ID, the same relation, the same cardinality, 1 to many, save it. Now we have the relation between those 2 tables. So after relating those tables, whatever you do here, you can actually create a chat with mixed data in those 2 views. I can select vehicle ID from this and select road type, or let's say road type from that. They will be connected because we connected the tables in the model view. That is how Power BI star schema connection works. Now we're done with the connection as well. The only thing left is to create a dashboard. From now on, it's totally up to you to leave or stay, because you already have the data and I've shown you how to connect Power BI to your data. So it is totally up to you. And if you want to create your own dashboard, you can. but I'm going to create a basic dashboard. So if you like the matrices and the charts that I made from those matrices, you can just stay and watch. So with the data that I have here, I'm going to use fact traffic table mostly to create the KPI cards and the rest of the dimension table data alongside with a few data from fact to create bar charts and a couple donut charts and a pie chart. So first, I'm going to create a KPI card using congestion level. And instead of sum, here I'm going to say average congestion level. Okay, that is expected because we generate the data. It should be close to 3, the congestion level. So here it is 2.81. Okay, we can create another KPI card as average speed using speed. Again, instead of sum, we pick average, and that is the average speed. That makes sense too, because that will be more likely the median of the values that the range that we selected for the speed. And we can create one more KPI card, the last one for, let's say, count of the vehicle IDs. Count distinct. So we have 30 vehicle IDs, mostly 30 records basically. We have 3 KPI cards from our data. Now let's create a bar chart. So choose cluster column chart and pick speed band and vehicle count from by vehicle ID and pick, not drag the vehicle ID to y-axis, shows count distinct and speed band. Oh, this is perfect. This is what I was trying to do. So we can see how many vehicles on average are going in each of the speed bands. Well, this data is not obviously these generated by us, so this doesn't represent any real life data. So we have that bar chart. Now we create a pie chart, maybe using zone type from the dimension zone and congestion level. And for the congestion, instead of sum, we have to pick average congestion level. So the blue one here is IT hub, and orange one is residential, which is suburb, and the purple one right here is transit hub, which includes airport and train station. And the turquoise one, the sky blue one, is commercial. So this is a perfect pie chart that we can use in the dashboard. And now let's create 2 donut charts. For the first donut chart, I'm going to use road types, since there are only 2 road types, city road and highway. And I'm going to pick speed and average the speed for each of the road type. Does this Does this donut chart make any sense? Well, I think it is better to represent it in a bar chart, but I think this works too, the donut plot. So we're going to create another donut plot and use the same parameter row type, but instead of speed, we use congestion level and average congestion level. Well, that is still pretty good. And we can create another bar chart. Oops. Another bar chart for all the road IDs to congestion level and make the congestion level to average congestion level to see which road has more traffic and which doesn't. So we can just compare them. And that's a good way to create a bar chart. And let's create another one for city zone and congestion level again. And again, average for the congestion level. So we can see which city zone has more traffic and which doesn't. That's perfect too. Oh, this is more perfect. That saves a lot of space. There you go. Now we have 3 bar plots, one horizontal and two horizontal and one vertical bar plot, and one pie chart and two donut charts, and 3 KPI cards that we created from this data. And each of them represent a unique set of data, and we can still create more data from these data, from more charts from these data. But I think this is enough. Haven't done too many calculations in this dashboard yet, but should I? Uh, I don't think so. I already done a lot of calculations in the silver and gold transformation itself. I think, yeah, I'm just going to rearrange these things with a good naming and stuff, just to make it look a better dashboard. Insert shape. And I'm going to use this. Shape. Rotate. I'm going to rotate it 180 degrees. Perfect. And place it right here. For the color, let me pick a color. Blue is fine, but yeah, blue is fine. I'll leave it. And for the name, insert text box, live traffic analytics dashboard. Make it bold and increase the size to maybe 24. Resize it to 20. 20 should be fine. Okay, and make this text box transparent. Properties. Color. Background turned off. Now that's perfect. For the text color, I'm going to pick white. Perfect. That should do. Now we have the heading for the dashboard. Now I'm going to make the KPIs look good. For all the KPIs, I go here. No, not the header icons. Turn the title on. Test should be average congestion. AVG. And that should be at the center of the KPI. And then we have category label. Turn that off. And then the background should be where is the background? Set the property title effects. Turn the background off, so that'll be transparent. Perfect. And do the same settings for all of them. Effects, turn the background off, title on. And the title for this should be average speed or speed AVG. That should be center of the KPI card. And turn the category label. Same with this. Turn off the category label. Title on. Total vehicles. Center. That should do for the KPIs. Now, let me resize every one of them to the same size so they fit perfectly. Properties. So let me copy this size to every one of them. Same. Copy. Perfect. So all the three KPI cards have the same dimensions now. I do that and that. Right under the KPI cards, I'm going to put these two horizontal bar charts. And the pie chart right here. For this, let me make this look good first. The title is on already. Say AVG congestion per city zone. Perfect, and make the heading center. Turn the title off for X and Y axis. We don't need it because just by seeing it, we can see which side represent the congestion level and which side represent the city zone. So we don't need that. The same thing with this one. We're going to edit the title first. Short it to average congestion per road to the center. And turn the titles off for X and Y axis. And for these two, should I leave the legends? Or maybe I leave the legends for one and turn it off for the other. Right? Like that. And for the title part, AVG speed per road type. That works. Format it to the center and okay, I have to deal with these decimal points. Back to the format. And data format. Not the row type, average speed. decimal number, decimal places to maybe 1. Now that looks perfect. Now the data is formatted. Let's leave that back into that position. Do the same with this one. Title AVG congestion per row type. Center it. We don't need to deal with this decimal points here for now, but if you got different data, you probably would have end up with more decimal point values. So we have to do the same thing. For average congestion, we say decimal number, decimal places to 1 or 2. It's up to you. We do that. And I'm going to make this thing larger to occupy all the space like that, and this one almost to occupy the rest of the space. And we just edit the titles of these two, and we're done. Average congestion by zone type. For this, count of vehicles per speed band, center it. Same thing with this, center the title. For this one, we hide the titles for the X and Y axis. Perfect. With that, I think this dashboard looks professional and looks good. Not professional, a basic dashboard that looks good. You can spend more time on the dashboard and to make it professional and use as much data as you can to visualize in this dashboard. But this one, I think, in my opinion, this is a pretty good dashboard. You can actually use this dashboard as well. I saved it. I will send this Power BI file as well to you guys. You can use it or you can create your own dashboard. Up to you. With that, we're done with our last step as well, which is Power BI dashboard creation. This one. Now, I'm going to have a recap of what we did in this project. Firstly, we got the data, which is our data source, through a Python code. We make the Python code to generate the data, which has false data in it as well. And this generated data will be streamed using Kafka as our data streaming engine. And the data that is streaming in Kafka will later be pulled out through Apache Spark, which will be our data processor in this project, pulled out, and a schema got assigned to that raw data, and still, while it is still in the raw stage, it is saved in the bronze storage layer as a delta table. We implemented delta lake, so the data that we store is stored as a delta table. And later, this data will be pulled again and cleaned and stored in the silver layer. Then later we pull the data out again, we create a few other tables, we split the tables into dimension and fact tables, and we do some extra modifications to the data and make the data business ready, and then save it in the goal layer. we initialized Hive Meta Store, the metadata database, by creating the tables that refers to these delta tables. And then we created three views for all these three tables, 2-dimension and 1 fact table. And later we established a thrift server for this database, and then connected this database through thrift server to Power BI, and pull the views into the Power BI, not the tables. And then we created a dashboard at the end. That is our whole data pipeline. That is the end of it. With that, we're done with this full project. If you like the project, don't forget to subscribe. With that being said, until the next video, adios.